Hi, this is David Van Vranken. Welcome to our 19th lecture here in Chemistry 51C during the spring of 2020. The campus is shut down and we're hunkering down, staying healthy, staying sane, and continuing to be interested in organic chemistry. I recently saw a vintage advertisement that talked about a compound called hexylresorcinol. And let's go ahead and see if we can watch that.
Take Sucrets, as many doctors recommend, for fast, temporary relief. Sucrets antiseptic lozenges help relieve sore throat pain fast. Sucrets contain the unique pain reliever hexylresorcinol. Unlike leading mouthwash and cough syrup products, Sucrets dissolve slowly, continuously releasing hexylresorcinol to bathe inflamed throat tissue. Sucrets kill germs on contact to help prevent infection, and Sucrets relieve sore throat pain fast. You can eat, drink, even smoke in greater comfort.
Man, are you thinking what I'm thinking? This guy's smoking 10 packs a day and getting a sore throat. Is there something simple he could do to help that sore throat? I got nothing. I can't think of any. I guess he better go buy another package of Sucrets. This gives us an opportunity to talk about hexylresorcinol. Why would they be putting that into these throat lozenges? Okay, here's the structure of hexylresorcinol. It's actually 4N-hexylresorcinol is the name for that compound. And it's prepared through two types of reactions that you know a little bit about. The first reaction is a variant of the Friedel-Crafts reaction that generates acylium ions. And as you know, hydroxy groups are ortho para-directors, and so you'll end up going preferentially ortho to one of these hydroxys and para to the other group. This is a very special variant of the Friedel-Crafts reactions that we don't learn about here in the Chem 51C series, called the freeze rearrangement. It involves formation of an ester, and then at very high temperature, in the presence of a Lewis acid, it ionizes to give an acylium ion, which attacks the benzene ring. The second step you do know about, and that is the Clemmensen reduction. So industrially, they used a Clemmensen reduction to reduce this carbonyl group down to a CH2 group using zinc-mercury amalgam. And that's the way they used to prepare hexylresorcinol. I don't think that modern Sucrets contains hexylresorcinol anymore. There's a modern variant of that, of the anesthetic that numbs your throat, I think called diclonine. Let's go ahead and continue where we left off on Wednesday, talking about the chemistry of aldol condensations, which is, boy, the idea of making enolates and having them attack carbonyl groups just seems so natural to me. That's really, we're really getting closer and closer in this course to what modern organic chemistry is about. It's not about SN2 reactions. It's about making enolates, it's about making carbon-carbon bonds, and it's about attacking carbonyls. All right, again, the chemistry that we talked about on Wednesday, we introduced the concept of the Aldol reaction, generating enolates alpha to carbonyl groups. So for example, if we had aldehydes and we treated those with sodium hydroxide, we would generate enolate anions, and those enolate anions would then attack carbonyl groups, and you protonate the alkoxide intermediate that you generate. That's pretty easy to understand. One of the issues that comes along with that is the issue that you really need to know whether you're going to eliminate that hydroxy group through this new mechanism that we talked about called an E1 conjugate base, E1CB elimination mechanism. And I told you that in the presence of heat, you can assume that you're going to lose the hydroxy group that used to be at this position. You need to know how to use this reaction. You need to know how to think about it backwards. You need to know how to think about it forwards. That's really critical for you to walk away with this chapter. I promise you, every single organic chemistry section here at UC Irvine and at other institutions will be asking you questions about the aldol reaction and the aldol condensation reaction. So get used to this idea that you make enolates alpha to carbonyls by deprotonating H's that aren't drawn for you. This is super hard to, if you're not really good at seeing all the H's that aren't drawn, it's going to kill you in this chapter especially. because we're going to be making bonds by replacing H's, and you just have to know that they're there. You have to see where all the H's are. One of the tricky things that I find is that people have a hard time thinking backwards. If I tell you you're going to make this product over here, this cyclopentenone, and you suspect that it's an aldol condensation, I expect you to think backwards, that the carbon atom next to the carbonyl is the one that used to be the enolate. So, and of course, somewhere in the mechanism that attacked the carbonyl. Sometimes I see that people work backwards and think, oh, well, maybe I could have generated that by attacking this carbonyl. And that's the wrong kind of thinking, because I'll just write a pH here, because that would mean you'd have to generate an anion over here, and that's not next to a carbonyl. You have to practice working problem after problem after problem in order to see what's going on. Okay, let's go ahead and move forward with these reactions where we make enolates and we use them to attack carbonyls. So I've shown you a kind of common type of aldol, a kind of simple version of the aldol condensation, where one aldehyde forms an enolate and attacks another copy of the starting material. But let me introduce you to a concept that you can have one carbonyl compound for making the enolate and then a different carbonyl compound that gets attacked. And we refer to these as crossed aldol reactions, where the carbonyl group that gets attacked is different from the carbonyl group that's forming the enolate. So what is it that makes a good crossed aldol reaction, a useful crossed aldol reaction? If you want it to be synthetically useful and give you high yields using two different carbonyl compounds, it's really effective when you try to attack aldehydes that don't have alpha CHs. Let's take an example. Here's an aldehyde that has no alpha CHs. This is called pivylaldehyde. And because it has no alpha CHs, we don't need to worry about accidentally forming an enolate with this aldehyde. The only enolate we're going to form is with the other reaction partner, the other carbonyl compound. So that kind of rules out one of the many possible side reactions you get in this reaction. We don't want to be forming enolate with our aldehyde and having it attack another aldehyde. So this limits the number of possibilities. So if you want effective yields, you want to make sure that one of your carbonyl compounds can't even form an enolate. So crossed aldol condensation reactions, this would be a good recipe for making that happen. So the product of this reaction would be, if you follow through what we've been saying, notice that I've got the delta symbol here, so you should assume that that's going to mean heat in this reaction. I'm not sure why I'm using blue, it just looks kind of satisfying here, to have that blue color. Here's our carbonyl group, and again, there's actually 3 CHs here, but we're going to lose 2 of those in this aldol condensation reaction. And so here's the product of that reaction. There we go. You actually get a mixture of E and Z enolates in this reaction. But we didn't have to run into any problems where we formed an enolate over here and had it come back and attack the ketone. Let's go and talk about mechanistically what's going on. I think you can kind of see the process that's going on here. As I mentioned before, the reaction is going to start off. I'm not going to draw out this whole arene ring. I just put the bromine there to try to make it a little more interesting. But the reaction is going to start off where you form an enolate. I'll go ahead and draw that here. You pull off a proton with the sodium hydroxide. I don't really need to draw out that mechanism. The hydroxide deprotonates one of the protons. And then that then attacks the carbonyl. So let's go ahead and draw out that process. And you just have to get used to attacking carbonyls. I hope we've done enough of that this quarter, where you can see that the process that's going to happen is that the carbanion will attack the carbonyl. Just like Grignard reagents attack carbonyls, just like alkylithiums attack carbonyls, just like alkynyl sodium reagents, acetylide anions attack carbonyls. This is the way organic chemistry works. And so you generate a new carbon-carbon bond. I'm not going to draw the protonation step with arrow pushing, but after you deprotonate with sodium hydroxide, you generate the conjugate acid from your base, that would be water. But I'm not going to draw that second protonation step. And remember, there's a subsequent elimination under these conditions because we're heating. I'll draw it for you, right? Normally we don't draw CHs. I'll draw that CH for you, but the next 2 mechanistic steps involve deprotonation by your base, not E2, it's not simultaneous, right? The next step of this process is going to be deprotonate, push the electrons up to the carbonyl, and there we go. That generates an enolate that then pushes out the hydroxide. Again, I know you were taught, don't use hydroxide as a leaving group. That was only for SN2 reactions. Well, SN1 also. But for E1 conjugate base, if you have any kind of an anion, an oxygen anion here, and a nitrogen anion, a carbanion, that will easily push out that leaving group. No problem with that. Okay, so what kinds of aldehydes are good in crossed aldol condensations? What are some examples of aldehydes that don't have alpha CHs, right? You have to start with some sort, if you want to do a crossed aldol condensation, some examples of aldehydes that you'll see commonly used. Let's go ahead and start with one of them. First one we'll draw is formaldehyde, right? In order to be an alpha CH, you have to be attached to an alpha carbon. There aren't even any alpha carbons on here. The H's that are directly attached to the carbonyl cannot be pulled off by any base that you could ever think of, right? Everywhere else we've been talking about H's attached to a carbon atom. These are called, that's the alpha carbon, and these are alpha CHs. Having an H directly attached to a carbonyl is not, you can never pull that off. Don't even think about that. Here would be another aldehyde that would be great for a crossed aldol condensation because it does have an alpha carbon, but like I showed you up above here, there's no protons on there. There's nothing for you to deprotonate, and you can't pull the proton off of the aldehyde carbonyl carbon. That proton is not acidic in any way, shape, or form. Here's another great aldehyde for you doing crossed aldol condensations. It's benzene, benzaldehyde, this benzene derivative. And again, there's no, right here at this position next to the carbonyl, there's no H's. So you can't deprotonate benzaldehyde and make any kind of an anion. So about the only thing you can do is make another anion and have it attack benzaldehyde. And the last one is a little bit weird. This one does have an alpha, and the last class of aldehydes you'll commonly see used in crossed aldol condensations does have an alpha CH, but you can't pull it off. I'll just draw it in a different color. This aldehyde proton that's alpha here, because it's attached to an sp2 center, if you tried to pull that off and use the carbonyl to delocalize that carbanion, it's not very effective. You get this weird looking structure with 3 double bonds all in a row called a cumulene. And so I'm simply going to have to tell you that proton there, it's not acidic. LDA wouldn't pull that off. None of the bases you know about would pull that off to make that kind of a weird looking cumulene type intermediate. So these are the common aldehydes that you'll see used for crossed aldol condensation. Again, the common theme here is they don't have any hydrogens attached to alpha carbons. We call those alpha hydrogens. We don't call the H attached to the carbonyl an alpha hydrogen. That's because there's no useful chemistry that we teach you how to do with that during this quarter. Wow, we're making enolates, we're attacking carbonyls. That's exciting. Man, it just feels so good and so natural to be doing that. That's what nature does. That's how nature builds carbon-carbon bonds and lipids and fats and long organic compounds. Okay, so again, as long as there are aldehydes present when you're doing aldol conditions, if you generate some kind of an enolate and it has a choice to attack either a ketone or an aldehyde, the aldehyde will be attacked faster. You don't have to worry about ketones attacking themselves as long as you have aldehydes present, because aldehydes are so much more reactive. So here's an example where the mechanism involves formation of this enolate intermediate on this ketone. You can't deprotonate here on benzaldehyde. There's no alpha carbon, there's no that has protons on it. So the only enolate you can make in this case, because the other side has a T-butyl group there, the only enolate that's possible under these reaction conditions with these two reactants is the one derived from this particular CH3 group next to the carbonyl. So you don't have to worry about, I'll just write out, you don't have to worry about some sort of self-condensation reaction where where a molecule of the ketone enolate attacks itself. And notice that the conditions are heating, so you can just presume that there's going to be, you don't have to worry about this. This is not formed in the conditions of the reaction because it's faster to attack another molecule of an aldehyde than it is to attack a ketone molecule. And that's not because this is hindered. If it was just acetone, it would still attack. This is the preferred pathway, not attacking the carbonyl of a ketone. Ketones are less reactive than aldehydes. They're less hindered. They have fewer, just like a secondary carbocation, they have fewer alkyl groups donating into the carbonyl carbon. Aldehydes are more reactive than ketones. And this is just a general principle that's, so let me come back to and just try to draw that explicitly. I'll draw the resonance structure here just to be a little bit different. I know the book doesn't often draws this resonance structure. So again, given the choice to attack a carbonyl, in this case, right, this would be slower. This process of attacking a carbonyl would be slower, slower, slower. Wow, ketones are just less reactive. Aldehydes are so reactive. That would be a slower process. Let me just write slower. There we go. Whereas attacking an aldehyde is just so much easier. The same enolate that's floating around in those reaction conditions, every collision with an aldehyde has a much higher chance of forming a carbon-carbon bond. And so let's go ahead and draw that process out where we attack it. That's not to say that it's impossible. It's not impossible for an enolate to attack a ketone. It's just faster. If it's 1,000 times faster to attack an aldehyde, then you're going to have 1,000 times more of this product than this other one, and you can't even isolate. You wouldn't be able to see something that's present in 1/1000th the ratio. So that's awesome. So crossed aldol condensation. If you want a ketone, ideally, if you want these are the kinds that I would usually depict. Is if I were to draw a crossed aldol condensation, I would pick a ketone that either gets deprotonated only on one side or where both sides are symmetrical. And I would put in an aldehyde that has no alpha CHs, and that would really narrow down the number of possible products. All right, let's come back to this, to aldol reactions, but involving 1,3-dicarbonyl compounds. I gave you guys a pKa table when we talked about making enolates and then alkylating them in that last chapter. And I said that when you've got two carbonyl groups attached to the same alkyl group, they really acidify those CHs there that are attached to that. So if it's easy to deprotonate when you have one carbonyl group, it's way easier to deprotonate when you have two carbonyl groups on that same CH. This compound right here, this is called diethyl malonate, has a pKa. Those protons in between have a pKa on the order of about 13. That's more acidic than water. More acidic than water. So you have no problems deprotonating this with sodium ethoxide or some other alkoxide base. This would be the base of choice. We'll talk in detail about that. And so it's very easy to do aldol type condensations with 1,3-dicarbonyl compounds, such as aldehydes. You want to pick something here that doesn't have alpha protons on the alpha position. So I'll pick benzaldehyde again. And so we have this pattern again where we have a carbonyl and the issue here is this going to eliminate, or is this going to, well, this would end up generating a conjugated double bond. And I told you if it can eliminate to form a conjugated double bond, we're not going to write heat in those conditions because it's usually spontaneous if you can eliminate to generate a conjugated double bond. Look at all this conjugation from this benzene ring into the carbonyl. Okay, so 1,3-dicarbonyls can easily do these types of aldol reactions. We've talked about before, just kind of briefly, that a nitrile group is similar to an ester group in terms of how much it acidifies. how much it acidifies the protons that are alpha to it. So you would expect, I would expect very similar reactivity for this beta keto ester and this beta keto nitrile. Both of these groups would acidify the CHs. I'd expect about the same pKa, more acidic than water by having a nitrile or two nitriles on each side. And so if I carried out the same reaction here, using these two, kind of like a crossed aldol condensation, again using sodium ethoxide, then I would expect to get that same sort of a condensation reaction. So whenever I see nitriles, I kind of think of them like esters, easy to make, or you can deprotonate alpha to them, not as easy as an aldehyde or ketone, but no problem deprotonating next to those. And this would do a condensation reaction. I've got to be a little bit careful here because there's two possible isomers, E plus Z. And I think the higher priority group is this one. So this is the E isomer. So I'll just write E entgegen. So you'd also get the Z isomer where the phenyl group was trans to the nitrile group, or the phenyl group was cis to the higher priority carboxy group. That's a little bit tricky with that stereochemistry issue. I hope you're really geared to think about RNS configurations as a form of stereochemistry. But as we come back to these chapters where we make E and Z isomers of olefins, like through the Wittig reaction or sometimes the Aldol reaction, you have to pay attention to the fact that you don't get any good control when you make these, well, at least in the reactions that I'm showing here, you don't get good control for E and Z stereochemistry. And so I'd like you to acknowledge if you think there's an E or Z stereoisomer situation there. Wow, it is just so easy to deprotonate when you've got two carbonyl groups attached to the same methylene, or a nitrile and a carbonyl group that's kind of conceptually the same kind of function. Okay, I've been showing you cases where we use a weak, we use a not strong base like an alkoxide. If I go to one of my colleagues and I talk about the word strong base, none of them would think about ethoxide as a strong base. We think strong base, LDA. That's a strong base. And hindered, man, right? If you really want to have control over your aldol reactions and make one and only one enolate, don't have protonation and deprotonation in equilibrium. So if you wanted to make this enolate and only this enolate, and I'm showing you that there's a lithium counterion here, then the way to do that is to take, for example, the ketone and then deprotonate that with LDA. Do you remember our recipe? LDA, THF, minus 78 degrees. That's our formula, and it deprotonates, the two sides of this ketones, alkyl on both sides, have about the same acidity. So as long as both sides have about the same acidity, LDA is going to go for the least hindered side. And that's the side with no extra methyl groups attached on there. So again, I think the book would often draw this out, these enolates out, using this resonance structure. And you might sometimes see the O attached to the lithium. And either one of these representations is fine. So if you make lithium enolates, you generate lithium disopropylamide in the laboratory in the morning. You have to make that yourself, unfortunately. And then you throw your carbonyl, or you drip your carbonyl compound in here, and you get 100% yield of the enolate. And as soon as you're done dripping that in, you're ready to add your aldehyde. You add your aldehyde in, and you get an aldol reaction going on. The first product that forms under these reaction conditions, let me go ahead and draw out the arrow pushing, is going to be an alkoxide intermediate. So you have to do an aqueous workup on these in order to protonate the intermediate. So there has to be a second step in here to add a proton if you do an aldol reaction using a lithium enolate. So we would refer to this as a directed aldol reaction. We're making an aldol, and then we're deciding what it's going to attack by adding in the aldehyde separately. So if you wanted to get a proton on here, we have to work this up. So I'm going to go ahead and write H2O work up. Right? Once you add your aldehyde in, you get this, and it'll sit there in your flask all afternoon. Don't let it sit all afternoon, but it would sit there all afternoon, and then you come back later and you mix it with some water and shake it up and extract the protonated alcohol, the neutral alcohol, into an organic solvent, and you evaporate that off. That's the way organic chemistry works. And so this is super powerful because knowing how to use LDA to make very specific enolates and high yield gives you this potential. So let's go ahead and walk through what we know how to do with LDA. So if we take some sort of a ketone like acetone here, which is pretty boring, and we deprotonate that using LDA, THF, minus 78 degrees. That's going to make the two sides are symmetrical, so we'll end up making an enolate on either side. It doesn't matter. But now we can alkylate that whatever side we form an enolate on, we can alkylate that. Let me use as an example allyl bromide. I love this alkylating agent because it doesn't have competing SN2 reactions. Just remember to keep your carbon count straight. So I'll go ahead and draw it alkylating over here on the right-hand side. 1, 2, 3 carbons are added. Again, I find a lot of people miscount the carbons and forget this CH2 group that used to be on the allyl bromide. You'd be super careful about that. I know you're thinking you're never going to make that mistake, but when you're rushed, a lot of people forget to draw that extra CH2, and I'm not going to accept that as an answer. I expect you to know how many carbons there are. When I draw allyl bromide, you're adding a 3-carbon unit. If we try this LDA process again, right, it will now deprotonate on the other side because that's less hindered. Both of these sides have about the same acidity. It's a ketone on both, with CHs on both sides. And so if we repeat this process of LDA, THF, minus 78 degrees Celsius, and now we can do an aldol. We could have done an aldol reaction first time, but now we can do an aldol reaction. Or we could alkylate again on the other side if we wanted. I'm just trying to take advantage of this new directed aldol process. And so let's go ahead and throw in an aldehyde. Looks to me like I'm using benzaldehyde again. Maybe you're getting bored of the benzaldehyde. So we throw in benzaldehyde, but we love benzaldehyde because there's no way to deprotonate on accident at the alpha position with benzaldehyde. Now, initially when you make an enolate here and it attacks the benzaldehyde, you're going to have an alkoxide. So we have to remember to do that aqueous workup here. So H2O, and I'll write the word workup. You don't have to do that, but I like to do that so you know I'm not trying to hydrate the carbonyl or do some other thing. So this generates after the water workup, you swamp it with water, you protonate your alcohol, and now you can extract that into an organic solvent, evaporate that off. See how much control you have? I just feel like as soon as I've done this stuff, I want to protect that OH as a tert-butyl dimethylsilyl group and then start doing Grignard reactions with the carbonyl and then start doing hydroboration oxidation of the alkene or addition of Br2 or addition of HBr and then make a Grignard. There's so many things you can do with this with these functional groups, right? There's also an arene ring you could start messing around with using electrophilic aromatic substitution. The number of different reactions that you can do. You can see how many possibilities there are if you like engineering and building molecules, building medicines, building new materials. You're starting to get a repertoire of reactions at your disposal for doing organic synthesis. But you've got to practice those tools. You've got to practice working problems to make those work. Rings are so common in nature. Rings are so common in designed drugs, in designed molecules, and I often ask you problems that involve formation of rings, and I need you to know how to use aldol reactions to make rings. I need you to know how to use carbonyl condensation reactions to make rings. Super important. And so these are some of the most important variants of enolate chemistry, or the ones that cyclize to form rings. So here's an example of a product that you can make where you form a ring. And so I'd like you to be able to work backwards with these. As soon as I see this, I can see I've got a carbonyl with alpha beta unsaturation. It just is telling me I could have made that using an aldol reaction. So I hope, like me, you're thinking, wow, I could have made that using an aldol reaction. And the key is for you to figure out what bond forms using an aldol, and in this case, it's a condensation. That's the bond right there that you would form. And you just need to know when you work retrosynthetically, when you go backwards, which of these two carbons should have been the carbonyl group. Right? In this case, since this is the carbonyl, it's this carbon over here that would have been deprotonated. So you have to draw that out. Right? That's the carbon over here that would have been deprotonated. And this other carbon down here, that's the one that would have been attacked and must have had a carbonyl. And you can see this is kind of tricky because this benzene derivative is symmetrical. There's an acetyl group up over here at 2 o'clock, and then there's an acetyl group down at 4 o'clock. So it doesn't, in this case, it doesn't matter which side gets deprotonated. Both the top and the bottom ketones, the alpha positions are non-distinguishable. Now, what base would we use? Well, we don't have to think very, very deeply about what base. You could use sodium ethoxide, sodium hydroxide. There's no side reactions with any of those that we have to worry about. I'm going to go ahead and use sodium ethoxide as a base. Why not sodium hydroxide? You know, I like things that are soluble. Sodium hydroxide has poor solubility in most organic solvents. And in this case, I'll write heat, but we wouldn't really have to write heat here because the product is conjugated. And I told you that if you have a potential to do an aldol condensation and eliminate the beta hydroxy group through an E1CB mechanism, you don't necessarily have to heat those. You don't have to show heat as a reagent. In this particular case, they heated it, maybe just to get it to go faster. Okay, so you need to be able to work backwards and forwards with intramolecular aldol condensations to make rings. You need to master this reaction by practicing it a bunch. Let me go ahead and show you a general principle for doing intramolecular aldol condensations. I'm going to go ahead and take an example of a dicarbonyl compound, where in theory there's more than one possible choice for the aldol reaction. So, right, you'll notice, so the two carbonyl groups are identical. It's just a long chain with ketone groups, you know, one atom away from the end of the chain. And so, but with each of these ketone groups, you could deprotonate either at this position here or at this position here. And they have about the same acidity. If you're using LDA, you can control the deprotonation, but when you're using a base like sodium ethoxide, you're going to get deprotonation here, deprotonation here, deprotonation here, methyl, CH2, CH3, CH2. It's all going to be in equilibrium. You can't really control that if you're using a base like sodium ethoxide. And so as soon as you form an enolate, for example, up here, it can actually get reprotonated, or it can attack the carbonyl. Let's follow the fate of that. What would you get? What size ring would you get if we attacked this carbonyl and then did an aldol condensation? So I'll just write, let me go ahead and write it in black here. But if we use those conditions up above, sodium ethoxide and heat, if we attack here, let's try to enumerate these carbons to make sure we don't make a mistake. What size ring are we going to generate? All right, 1, 2, 3, 4, 5, 6. And then we're going to have a methyl group hanging off of carbon 6. Let me go ahead and draw those out here. Maybe I'll try to keep as many of these carbon atoms in the same position. I got 1, 2, 3, and 4. But if I want to make a 6-membered ring, I'll just go ahead and draw it. Carbon 1 is going to do an aldol condensation. Let's go ahead and make sure we enumerate these carbons. There's carbon 1. There's carbonyl group number 2. Here's CH2 group number 3. There's CH2 group number 4. And CH2 group number 5 is sticking up. The carbon number 6 that has no protons on it, that's over here. And sticking off of that, I said there's going to be a methyl group that doesn't undergo any changes in chemistry. That would be the product of this reaction. And you might have to find yourself doing atom mapping, enumerating groups, CH2s and CH3s in your starting materials, and matching them up with CH2s and CH3s in your product to make sure you write out the correct product in this reaction. Now, it is perfectly possible, and it is happening in this reaction, that you are also deprotonating down here on carbon atom number 3. And why don't we get any aldol products from that, any aldol condensations. Let's take a look at what the fate of that would be. In this case, if you have a chance to form a 5-membered ring or a 6-membered ring versus a smaller ring size, like 3 or 4, you're not going to get the 3 or 4-membered ring. You're certainly generating enolates by deprotonating there, but they simply get reprotonated again because it is so hard to form a strained 4-membered ring. That is difficult. Man, there's like 26 kilocalories per mole of ring strain in a 4-membered ring. So you might think in theory, oh, how come I'm not getting this this other ring size? Boy, how do I even draw this here? I'm going to draw it like this. If I try to draw this condensation product out, it's going to be all wacky looking. Here we go. This is what we would end up generating. Again, it's 1, 2, 3, 4, 5, and 6. So I've still got 1, 2, and 3 here, and 4, and CH2 group number 5. And here's that carbonyl with no H's, number 6, and the methyl group hanging off of that. That's not going to form. I'm just going to say not formed. If you can form a 5 or 6-membered ring through an aldol condensation, you're not going to get the product for formation of smaller strained rings, like 3 or 4. It's not going to happen. And people have done zillions of intramolecular aldols to make 5 and 6-membered rings. If you go back and you look at the research literature of the 1950s, boy, this was like the money reaction of those days. Right before those secrets commercials were coming out. That was the chemistry everybody was doing. It was making 5 and 6-membered rings using aldol reactions. All right, let's go ahead and take a look at another variant of this aldol chemistry. And we're going to talk about esters. It adds a little bit of complexity here when we're working with esters. So there's a reaction where you do something like an aldol condensation reaction, but we do it with using ester starting material. So I'll go ahead and show you a reaction here, which may seem a little bit strange because I'm only going to draw 1 molecule of the starting material, but I want you to remember when I draw ethyl propionate like this, so it's not ethyl acetate, it's propionate with 3 carbons on the carboxylic acid moiety. You have to remember that there's more than 1 molecule in solution. So even if I didn't write another molecule here, you can see that I've used at least 2 molecules to generate the product. Really, when you run a reaction, you have closer to 6.02 times 10 to the 23rd molecules in your flask. So it isn't weird that you can draw a product that has involved 2 of these molecules. Now, we have to be super choosy. If we want to make enolates with this Claisen reaction, boy, this is a really old reaction. It probably goes back to the early 1900s. We have to be super careful about our choice of base. And it turns out that our choice of base has to match this carboxy group over here. So if we have an ethyl ester, we have to use either sodium or potassium alkoxide. Sodium is the common one. We have to make sure that our alkoxide base, let me use the red pen here, matches our ester. And I'll explain that in a second. Okay, so with a base, the base is going to be generating enolates. It'll deprotonate over here, alpha to the carbonyl. There's protons there. And those protons are going to do a substitute. The enolate is going to attack another ester and substitute it. You can see that we've substituted an ethoxy group here. So the byproduct in this case is going to be another ethanol molecule. Now I have to show the workup reaction here. You can't just stop here. And this is going to be critical, is that we have to draw in a workup. And it's not just water. I'll come back to this later, but we have to use an aqueous acid workup. Don't just write H3O plus, right? Aqueous HCl, write a real reagent. When I draw transformations with reagents, I want real reagents, not B. That's for arrow pushing mechanisms, not HA. That's for arrow pushing mechanisms. When I'm talking about chemistry that give real products with yields and things that you isolate with no curved arrows, I want real reagents. So hydrochloric acid is fine. Sulfuric acid would be fine, but it's aqueous HCl, and this is just for a workup. And what's the workup for? The workup is for protonating this. Now, the product here is, there's this new stereocenter. I'm not going to draw the configure. I'll just write racemic to indicate that. Boy, whenever you generate a new stereogenic center, you home in on that and note the fact that there's a stereogenic center there. I might as well draw a stereochemistry on that, the proton going up. Traditionally, we would draw something else dashed, something else that's next to this H in a dash form. So it's racemic, so there would be plus, plus the other enantiomer plus E. Okay, why are we being so picky? What's the reason why we need to be picky about our choice of the alkoxide base here? Let's go ahead and talk about stuff that's happening in solution that you can't even tell is happening because we chose carefully with the base. If you take an ethyl ester of some kind and you add an alkoxide base, like sodium ethoxide, it is deprotonating at the alpha carbon. It's deprotonating, reprotonating, it gets deprotonated, but there's another reaction that's occurring that is completely transparent to you, and that is that some of the time the alkoxide is attacking the carbonyl. You can't stop that from happening in this reaction. So quite often it deprotonates, and every once in a while it's attacking the carbonyl, and that could be disastrous, except if we've carefully chosen the alkoxide base to match the ester, we end up in a situation where through our careful choice of base, we've set it up so it won't matter that we've attacked the carbonyl, because now when we push out the leaving group, these are both going to be identical. So if we kick out the alkoxide base that just added, it doesn't matter. Or if we if we kick out the original ethoxy, it'll give us exactly the same thing. There's no difference here. We do not change our alkoxy, we don't change our ester by accidentally attacking. And I say accidentally, you can't avoid this process. And so this is occurring under the reaction conditions. It's going back and forth where, and then this comes back in and brings you here, and then it goes there. So you can't stop your alkoxide base from attacking your ester. You can't stop that. So you have to make sure the alkoxide matches the original ester alkoxy group so that you won't end up exchanging a methyl ester for an ethyl ester, or if you use sodium hydroxide, you would just simply hydrolyze your ester. You would not get any of this. The hydrolysis, the saponification reaction would be faster if you used hydroxide as a base to try to do this Claisen condensation. Okay, choose carefully your base when you do these Claisen reactions. That's super essential. Let's go ahead and talk about the mechanism of this Claisen reaction. I think it's kind of obvious. It's very similar to the mechanism for the aldol chemistry that we've been talking about. So if I draw out a Claisen reaction of ethyl acetate, here we go, and I've very carefully chosen my base in this case to do a Claisen reaction. I've made sure that it matches. The ethoxide is definitely attacking the carbonyl. You can't stop that from happening, but every once in a while, it's going to deprotonate that proton at the alpha position and generate an enolate. This is not a very easy enolate to generate. Esters are about 100,000 times less acidic at the alpha proton than a ketone at that position. So it's going to generate some of this enolate, and then that enolate is going to attack another ester molecule. So here's our ester enolate. We'll generate a small amount of that ester enolate in solution. Very small amount, maybe 1 out of every 10 billion of these molecules exists in this enolate form. But you usually use the ester as the solvent for the reaction. So the chances of colliding with another ester molecule are actually very good if you use your ester as the solvent and the reactant for the reaction. And so you end up forming a carbon-carbon bond. Let me go ahead and draw out that intermediate. Whoops, let me switch over to the black pen here. There's our tetrahedral intermediate. And now we've got this ethoxide, right? We've got this anion here. No problem pushing out that ethoxide leaving group. Again, this ethoxide is not a leaving group for SN2 reactions, but in this case, because there's an anion right next door here, you can't stop that from getting pushed out as a leaving group. It's unstoppable. It's so facile. When you have either a carbanion here or an N- or a C-, that's just really facile. So when we push this out, we're going to regenerate a carbonyl. And we have to pay careful attention to the leaving group that we just generated, because this ethoxide leaving group, under the conditions of this reaction, is basic. It's just as basic as it was. And if we were able to pull off a proton in the beginning, right, look at this 1,3-dicarbonyl, it's even easier to pull it off now. Again, these CHs are more acidic than water. More acidic than water. The pK of this is about 11. It's about 100,000 times more acidic than water. So you cannot stop this from deprotonating. And so the final product of the reaction is not this 1,3-dicarbonyl compound. What's sitting in your flask at the end of this reaction is this stabilized enolate, which if you wanted, you could do SN2 reactions if you threw in an alkyl iodide. Generally, we just work these up. And you might think, oh, it's a carbanion, I have to protonate it. No, you can't protonate this with the ethanol. That's the wrong direction for the equilibrium. The equilibrium lies in this direction, not this direction. So this is the product at the end of the reaction. If you started with sodium ethoxide, you'd end up with the sodium salt of this. And so this, we finally have to do some sort of a workup on that in order to protonate this. So this is the product before the workup. Before we work this up, this is what's sitting in there. And it'll just sit there. It'll just keep on sitting there and be perfectly happy. So let's go ahead and take a look. What do we have to do to get a proton on there? We better pick something more acidic than water. We can't just write H2O workup, because that would be wrong. That thing would just sit in water and kind of laugh at the water. Not going to do anything. Man. So we've got to work these reactions up using something acidic like aqueous hydrochloric acid. So the recipe for a Claisen reaction is you typically use your ethyl acetate or your ester in a big excess. You throw in a base, an alkoxide base, that's the Claisen recipe, and we can't use sodium methoxide. If it was a methyl ester, I would use sodium methoxide. If it was a isopropyl ester, I would use isopropoxide anion or sodium or potassium isopropoxide. In this case, again, it's an ethyl ester. Those are really common. They're more common in organic chemistry than methyl esters. So sodium ethoxide, I guess the world loves ethanol, so maybe that's why ethanol and ethoxide anions are so common and inexpensive. And so this is what you initially get before you do your workup, is you end up with this anion in solution as the sodium salt. So let me go ahead and draw this out. I'll draw the sodium counterion over here. And there's that carbanion that looks like it's easy to protonate, but you've got to use an acid for this. And so the workup conditions that you need are HCl, aqueous HCl. I'll write the water instead of writing AQ for aqueous. These are the workup conditions. So you can't just use H2O because, right, if I tried using H2O workup, H2O, it won't protonate it. It just will not protonate it. I'll just write no reaction here. So these are the workup conditions that you need for, I didn't leave enough room there, so a little bit worried about that. These are the conditions you need, an acidic workup here in order to isolate this beta keto ester that you generate. Now there is a reaction that they talk about in the book where you take one type of ester and you get it to add to a completely different type of ester using basic conditions. That's called a crossed Aldol condensation. Those are really picky. It's so rare that you can get those to work. I'm not going to ask about it on my exam. Kind of cool to read about. It'll reinforce your knowledge of the Aldol, of the Claisen reaction. But I don't ask about crossed Claisen reactions on my exam. There is a version of the Claisen reaction that's intramolecular, but we don't have time to talk about that today. When we come back, I'm going to talk about intramolecular Claisen reactions to generate 5- and 6-membered rings. It's got a completely different name, and those work amazing. They're actually way more common than this acyclic intermolecular Claisen reaction. All right, everyone. I'll see you on Friday. Thanks for coming to my lecture, and keep working lots of problems, and keep thinking about enolates, adding to carbonyls.